Now we'll discuss about this Kepler's second law, or it is also known as nothing but law of area. So in Kepler's first law, we discussed that all the planets are going to revolve around the Sun in an elliptical orbit in such a way that Sun is located at one of the focus. So if you are considering an elliptical path over here, and we know that this line is known as nothing but a major axis, and this line we call it as nothing but a minor axis, and Sun is located at one of the focus. Let's say this is the location of Sun, and the planets are revolving around the Sun in an elliptical orbit. So let's say this is the location of planet at this instant, and this planet is revolving around the Sun in an elliptical path, something like this. Now this Kepler's second law states that when a planet is revolving around the Sun in an elliptical path, then the line joining the center of this planet and the center of Sun will covers equal area in equal intervals of time. So just try to observe what is the meaning of this. Like in a time of t seconds, assume that or in a time t, the planet is covered from a distance from here to here, or from point 1 to point 2. So we can say that if you are considering the area covered by the line joining the center of planet and center of Sun, so we can say that this is the area swept by the line joining the center of planet and the center of Sun. Now we can observe that if you are considering the location of planet at some other point, let's say the planet was initially somewhere over here. So consider that at t is equal to 0, planet was over here, and in the same time of t seconds, same as like in the previous case, assume that planet is displaced from here to here. So we can say that again, if you are considering the line joining the Sun and the planet, so if you are taking the same time, then it should travel, or it should swept same area, or the line joining the Sun and the planet should cover equal areas in equal intervals of time. That means if you are taking same time, then this area and this area should be same. Or we can take one more example, like assume that for at an instant, but the planet was over here, and in the same time interval of t that we consider earlier, let's say this planet is reached somewhere over here. So this is the line joining the center of planet and center of Sun. So this is the area covered by the line joining the center of planet and Sun. So we can say that all these areas are same if you are taking same time interval. So this is known as nothing but Kepler's second law, or law of area. So once again it states that the line joining the Sun, the line joining the center of Sun and the center of planet sweeps out or covers equal area in equal intervals of time. Now just try to observe why it is covering equal areas and equal intervals of time. So here we can use in the previous part we discussed about conservation of angular momentum in planetary motion. So we can explain it while using the concept of conservation of angular momentum. So we know that if a planet is revolving around the Sun, Sun is located at one of the focus, let's say Sun is over here, and assume that at an instant the planet is somewhere over here. Now at this instantaneous location of planet, I am just representing over here. Now in a time of like in a small duration of time, let's say if you are taking a small duration of time dt, this planet will displace by some distance. Let's say the planet is displaced to a point somewhere over here. So we are going to just observe what about the area covered by the line joining the Sun and the planet in a small duration of time. Let's say planet is moving with the velocity v at this instant. So in a small duration of time dt, we can assume that this velocity is almost constant for a small duration of time dt. So it will travel a distance that is equal to v into t. So vt is the distance traveled by the planet in a small duration of time dt. We are just using that equation, displacement is equal to velocity into time. So for small displacement, we are writing v into small time, let's say dt. We are taking small time because if you are taking a larger time, then velocity is not equal to a constant. So this one is the line joining the planet and the Sun and the planet. And we can find out what about the value of area covered by this one in a time of dt seconds. So we can say that area covered by the line joining the center of Sun and the planet will be equal to area of this portion, or we can observe that we are able to get a triangular portion. So we need to find out the area of this triangular part. Now just observe how to find out the value of area of this triangular portion. To find out the area of triangular portion, we know that area of triangle is half into base into height. So height means this perpendicular distance is nothing but the height. So for the calculation of area, we need to find out the value of this h. So let's say let's observe how to find out the value of this height h over here. Now take it as the velocity vector. So at this instant, direction of velocity vector is along this direction. Let's say this velocity vector is equal to nothing but v, and the position vector means the radius vector or instantaneous position vector, that is take it as r vector, and the angle between them is equal to take it as nothing but theta. So definitely this angle should also be equal to nothing but theta. So we can find out what about the component of this Vt along this direction. Like I'm talking about this Vt. Vt is like, you can observe that there is a right angle triangle over here. From this right angle triangle we can write as this is Vdt. So this component is going to be Vdt cos theta, and this component is going to be Vdt sin theta. So we can write the value of this height h is equal to, from this right angle triangle we can observe that that is equal to V dt into sin theta. So now we got the value of perpendicular distance for that triangle, so we can find out the value of area of this triangle. Let's say I'm just considering area of this triangular portion is equal to dA. Now we know that this velocity, this area is equal to nothing but half into base into height. So we can take it as base of this triangle is nothing but this distance, and that we can take it as the position vector r vector. So distance from here to here, I'm just taking it as the instantaneous position vector or r vector. So this we can take it as dA is equal to half into base is nothing but r, and h is equal to, we can take it as v into dt into sin theta. Now our aim is to find out the value of rate of change of area, or the area covered by the line joining the sun and the planet in a time of t seconds. So we can write dA divided by dt is equal to, we can take it as half into v into r into sin theta. Now we can observe that in the previous class we discussed about conservation of angular momentum, and there we discussed that angular momentum of a planet is going to be a constant, and the equation for angular momentum was m into v into r into sin theta. So we can observe that as this term is equal to a constant, from here we can say that this value, that is Vr sin theta, the value of V into R into sin theta is going to be angular momentum divided by mass. So we can write, instead of this dA divided by dt, we can write this as half into this V into R into sin theta, we can take it as L divided by m. So if you want to find out the value of dA by dt, even you can use this equation. This is angular momentum divided by 2m, and we know that this angular momentum is a constant and mass of planet is also a constant. So we can say that this dA by dt is equal to a constant. That's why we are taking it is the area covered by the line joining the sun and planet per unit time is equal to a constant, or dA by dt is equal to a constant. So which we can find out by using this equation also, that is L divided by 2m. Now if you are considering a situation that a planet covers one full rotation, so that means if a planet is starting from this point and it's complete one full rotation, let's say total time taken for its rotation is nothing but t, and for this planet we know that this is known as its major axis, and the half of this major axis we call it as nothing but a semi major axis. It is represented by small letter a, and this is known as minor axis, and half of this is represented by semi minor axis represented by b. So we can find out what about the value of this dA divided by dt. Like when it's complete one full rotation, so the total area will be equal to the entire area of this elliptical path, and the total area of ellipse we can find out by using this equation pi ab divided by, and if it's t is a time period, that is time taken to complete one full rotation, so we can write pi ab by t is equal to nothing but L divided by 2m. Or from this also we can write the equation for angular momentum, that is L is equal to pi into ab into 2m divided by t.